Hi and welcome to this introduction on entropy. In the last lesson, we finished up looking at enthalpy. So we were looking at the enthalpy change of solution. We constructed a Born-Haber cycle in order to calculate the enthalpy change of solution using the lattice enthalpies and hydration enthalpies as well. And remember, we can use those cycles to calculate the enthalpy change of solution using an indirect route, for example. But in this lesson, we're going to move on to and introduce entropy. What is entropy? It can be defined as the randomness or the dispersal of energy of a system, as you can see from this image here. So the more disordered the system is, the higher the value of entropy. So in this image, there's a higher value of entropy on the right-hand side. Entropy is affected by the state of the matter, whether it's dissolved or not, and the number of particles involved. And in general, solids have a lower value of entropy than liquids, and liquids have a lower value of entropy than gases. And the arrangement of particles is to do with that, of course. Our gases, the particles are arranged more randomly than they are in liquids, and obviously in solids they are fixed very close together. Looking at dissolving, so when we dissolve a solid in a solvent, the entropy of the system increases. It's quite clear, it's because of the free movement of the particles. They can move so much more freely in that when they're dissolved in the solvent. And finally, we need to think about reactions as well. So in a reaction, if the number of moles of the product formed is greater than the number of moles of the reactants, then we will say that there's an overall increase in entropy. That is because there's an increased number of ways in which these particles can be arranged, and that is what entropy really means. We can look at this further. So we can say that if our entropy value is negative, it means that the entropy of the reactants was greater than the entropy of the products. And then the other way around, if it's positive, it means the entropy of the products was greater than the entropy of the reactants. In all reactions, the reactants and products have different entropy values. So we can use these values to calculate the overall change in entropy. And S is used to notify entropy. It's important to note that the higher the entropy of the system, the more stable the system is. Therefore, a substance will naturally move in order to increase its entropy. And you may well have heard people and physicists, for example, talking about the universe constantly expanding, and some of that is coming from this idea. Entropy values can be found in databases. Of course, they depend on what the compound is and what state they're in, and they're often listed in standard conditions. Here we're calculating the overall entropy change. So we're going to take our entropy change of our product and take away from that the entropy change of our reactants. A really important thing to remember for some of the questions we're about to come onto and the calculations is you need to remember the standard conditions. So 298 degrees Kelvin and 100 kilopascals. You'll have noticed in that last question that water and oxygen, their values had to be multiplied by 2, their entropy values. That's because when you looked at the stoichiometric ratio of the equation, there were 2 moles of those 2 compounds. It's really important that you multiply your numbers by, or your entropy values, by the number of moles that you can see in the stoichiometric ratio. That's because the definition of entropy is really important here. Entropy values are always given per mole.